Look at
3,
this.
6,
What do you see?
9.
To me, this is one of the most beautiful, fascinating, and frustrating things I've ever seen. That's because I'm a mathematician, and these hypnotizing curlicues have haunted people like me for 150 years. What we're looking at is a glimpse of the Riemann Hypothesis. It's one of the most important, if not the most important, unsolved problems in all of mathematics. You may have heard about the Riemann Hypothesis because it's one of the Millennium Problems of the Clay Institute. What that means is that the person who solves it not only achieves immortality in mathematics, but also wins a $1 million prize. But there are other reasons to care about the enigma that is the Riemann Hypothesis. If the hypothesis is true, it would solve a mystery as old as math itself. That is, the mystery of the prime numbers. Countless theorems in fields as far apart as cryptography and quantum physics assume that the Riemann Hypothesis is true, which means that we have a lot riding on this single unproven statement. So what is it? What is the Riemann Hypothesis? Why has the search for a proof become something of a holy grail for mathematicians? And what do these strange curlicues have to do with all of this? My name is Alex Kantorovich, and I'm a professor of mathematics. I'll serve as your guide as we explore the Riemann Hypothesis. In order to build a somewhat sophisticated understanding of this hypothesis, what I'm going to try to do is mention some slightly advanced concepts. Now, you don't need an advanced degree in mathematics to go on this journey with me. What I'm going to do is try to lay the groundwork, step by step, in a visual and intuitive way. So, to begin, let's venture into the chaotic and elusive universe of prime numbers. This is Factor City, where the primes are literally the building blocks of all numbers. Now, every whole number is a building, and it's been constructed out of its primes. The one-story houses are exactly the primes. Now, thanks to the ancient Greek Euclid of Alexandria, we know that the one-story buildings keep going on forever, if you can walk that far. But, depending on where you're standing, you might want to know, how many one-story buildings do you see around you? This is what we want to understand about the prime numbers and what we currently don't. You see, the prime numbers seem to just pop up randomly among the natural numbers, all the way out to infinity. In the late 1700s, mathematicians were really starting to wonder whether it was possible to predict the places where primes would appear. Now, a teenage boy named Carl Friedrich Gauss was especially obsessed with taming the primes. He calculated massive tables of primes, going all the way up to 3 million, and looked for patterns. We can see the data that Gauss collected on the prime numbers by using something we'll call the prime counting function. The graph of that function will show us exactly where the prime numbers appear as the numbers get bigger and bigger. So the graph stays flat until you hit a prime, and at that point it jumps up by 1. Here's what the graph looks like out to 10, and out to 100, and now out to 3 million, as far as Gauss went. At this scale, those bumps we saw early on have smoothed out, leaving a pretty pleasant curve. When Gauss looked at this data, he asked himself, is there some other function that I know that has pretty much the same graph? Now, as luck would have it, at around the same time, Gauss was also playing around with logarithm functions. You might remember that a logarithm is a function